Maxwell's equations, Gauss's law for magnetic fields. Hopefully you watched the previous lecture on Gauss's law for electric fields. Well, for magnetic fields, there is no charge. And so this means that the magnetic fields cannot begin or end because the electric fields, the positive charges were sources of the flux. The negative charges were sinks for the flux, so the electric field started and ended on the charges. Well, with magnetic fields, there are no charges, so the fields cannot start or end. Yet, they have to exist. This means they can only form loops. That doesn't mean they have to be circular loops. They could have odd shapes like we're showing here, but magnetic fields always form loops because there is no charge. There's no magnetic charge. So that means we can write Gauss's law like we did for the electric fields, but rather than put our electric flux density inside the closed contour surface integral, we will put the magnetic flux density. So in a way, this is calculating total magnetic charge, and that has to be 0. So how do we understand this being 0? Well, if the magnetic field always forms loops, it could be that that loop is completely contained inside the surface, and therefore the integral never sees the magnetic field. So of course that would add to 0. Similarly, that loop might be completely outside of that surface, and in which case, again, that surface integral would not see the loop. The only thing left over is if there's a loop that crosses the surface. Well, it turns out when it does that, it will have to enter the surface in one place and leave the surface at the other, and in the end it will completely cancel. So anytime the magnetic field forms loops and we do this surface integral, that integral has to be 0. The magnetic flux is always 0. And like we mentioned before, if the magnetic flux was not 0, that implies that there's magnetic charge present, which of course does not physically exist. So we arrive at Gauss's law for magnetic fields. It looks just like Gauss's law for the electric fields, but we're not seeing that volume integral of charge density because there is no charge density for magnetic fields. So this is it for Gauss's law for magnetic fields in integral form. Now, to get the Gauss's law for magnetic fields in differential form, we will use the divergence theorem the same way we did for Gauss's law for electric fields. So we start with Gauss's law for magnetic fields, and I've written it in a very general form where we're pretending that we have magnetic charge. So we're using the duality of electric and magnetic fields here. Then we apply the divergence theorem to this closed contour surface integral, and we get a volume integral of the divergence of B. And now we have two volume integrals that we're setting equal. So if we have these two volume integrals and they're equal, then the arguments inside of those integrals must be equal. And so we set them equal. However, in magnetics, there is no such thing as magnetic charge, and so we set that equal to 0. And when we do that, we arrive at Gauss's law for magnetic fields in differential form. The only difference between this and Gauss's law in differential form for electric fields is that we had a volume charge density here.